Hello all, welcome to this tutorial in which we shall be looking at GMMs. So in the earlier discussions, it is pretty much evident that the need of mixture models. In this tutorial, what we shall do is we shall take the Gaussian mixture models and then we will derive the closed form solutions for obtaining the parameters. So we will be using the exact same steps that are there in EM algorithm, but since it is easy for us to equate the expectation that is there to zero while optimization and then obtain the closed form solution, now we shall be doing that. Okay, so without any further delay, so let's further go into this. So EM with GMMs. So we all know that MLE. So we obtain theta star as argmax of theta summation over all the parameters log of p theta of xi. Okay, so here we are assuming that the data is x1, x2 till xn id from px. Okay. So in case of mixture models, the case of mixture models and assuming the densities are Gaussian, assuming the densities are Gaussians. So what are the parameter theta that we shall have? Now we shall have alpha j, which is the probability with which I'll be choosing. Assuming that there are m Gaussians, what is the probability of choosing the jth Gaussian? And mu j, which is the mean of the jth Gaussian, and then sigma j, which is the covariance matrix. I have j running from 1 to m. Now then, because of which my log likelihood, which I is equal to 1 to n, this is over the data, log of p theta of xi is equal to summation I is equal to 1 to n log of j equals 1 to m alpha j p theta j of xi. Okay, so this is, so normally what we used to do in ML estimate is we used to directly take this and go ahead, differentiate with respect to the parameter and equate it to 0 and obtain the equations. But now this is log of sums, so we cannot go ahead with that procedure as we have looked into. Now these are log of sums. Okay, so now you cannot do it, so Let's go into the EM algorithm. Now, before going there, a couple of pre things. So for any given xi, okay, so we can know that k equals 1 to m. You have m mixtures, alpha k xi from the parameter mu k and sigma k. And then it is clear that you're choosing z equals to k, you're choosing kth Gaussian, the probability alpha k, and then once you sum over k equals 1 to m alpha k, it has to be 1. Okay. Now this is the constraint. And then once you have chosen a specific Gaussian xi, given you have chosen the kth Gaussian component, now it will be a normal density which is parameterized by mu k and sigma k. This needs to be clear. Okay. So now recall from the EM algorithm, recall f theta of q is expectation over this q log of p theta of x comma z divided by q of z. Okay. So now when do we get the optimal value here? So we obtain the optimal value when q of z is p theta of z given x. Okay. When you put this, that is when you get the optimal value. So now it's easy for us to calculate. Now p theta of, you choose from the kth component given your input is xi. Now we can easily compute it using the Bayes rule. P of xi comma z equal to k divided by p of xi. Now this is equal to p of z equal to k, p of xi given z equal to k divided by, we have already obtained this component j equals to 1 to m, the mixing coefficient alpha j, normal xi parameterized by mu j and sigma j. This we can again alpha k, this is normal xi parameterized by mu k sigma k divided by summation j equals 1 to m alpha j n of xi mu j sigma j. Okay. So now it is easy to see that now if I sum it over if I sum it over k equals 1 to m, this component, okay, so sum it over k, okay, sum it over k equals 1 to m. Now this specific component, it will be 1. Okay, so this is pretty much evident. So let's call this term as k. Okay, so this is the probability that we are given the data point xi. Now what is the probability that it is coming from the kth Gaussian? Okay, so let's proceed. Now this is the optimal value. Now we just need to pitch it in here, pitch this value in here, obtain this expectation, and then do the maximization step. That's the overall thing. Okay, just write it down for the sake of completeness. The EM algorithm for t equals 1 to convergence q t plus 1 of z equals p theta t of z given xi. Okay, so now then once you have this, you compute f theta of q t plus 1. And what is this? This is expectation with respect to this t plus 1 of z log of p theta of xi comma z divided by q p plus 1 of z. See, now please remember that I'm considering only one data point. Now if you put all of them together, you will have a summation outside running from I is equal to 1 to n. That will be there. Okay, so this is your E step, and then the M step is theta t plus 1 equals to argmax of theta f theta of q t plus 1. You just repeat this. You compute this, obtain this, you get theta t plus 1, use that theta t plus 1 here, get theta t plus 2, obtain this, compute this. Now you go on iterating over these steps, okay, till convergence. Now the idea of convergence, see, when you see that there is no more updation, now that means that from the previous step and the current step is the difference between all the parameters is within some bound. That is when we prefer to stop. But there are multiple ways. Now you can even compute the loss that was in the previous step and the current step and see whether it is in the bound, or you'll just stop after some 100 iteration or some 200 iterations up to. These are all different ways in which the stopping criteria can be looked at. Okay, so now coming to the E step. Now I have computed this just now. Now pitch it in. Okay, now for the ease of notation, I am just removing this t. You obtain the parameters, then plug it in and go on doing the same thing. Okay, so you just reiterate the whole process for some amount of time or whatever feels the convergence for you. Okay, so I just want to reiterate the same thing. So now I have obtained the values here. Now I'll put them here into this step and then obtain f theta, and then what I'll do, I'll take the derivative with respect to the parameters, equate it to 0 and obtain the values. I'll get the new parameters, and then go back and reiterate. Okay, fine. Now the E step. I'm doing the E step now. What is E step? As I said, I'm not using that T Q expectation of Q of Z log of P theta of V comma Z. Okay, divided by Q of Z. Okay, you have chosen Z, you have fixed it. So then this will be expectation Q of Z log of P theta of V comma Z minus log of Q of Z. This will be expectation of Q of Z log of P theta of, oh sorry, okay, so small notational mistake. Now, this is not V, okay, I want it to be Xi, okay. Xi, ith value, okay. So now when do I get the optimal value? When I replace this with P of Z given Xi log of P theta of Xi comma Z. Okay, so now this I can easily obtain. This is summation over j equals 1 to m. This is probability that z takes the value j for even xi, then log of p theta of xi comma z equals to j. Okay, so now with this I can rewrite it as summation j is equal to 1 to m, just the standard algebra. P of j is, z is from the jth component, so log of p theta of xi given z equals to j plus log of p of z equals to j. Okay, now this I can substitute. I know this value, I know this, I know this. I can easily substitute all of them. So j equals 1 to m log of xi parameterized by mu j sigma j plus log of, okay. So now here this is your expectation. Yeah, there is one more summation outside, but now this has to be optimized under a constraint. Okay, this is a constraint optimization. Now this optimize this with respect to constraint such that now you therefore the final uh, expectation will be, I'll just call it as L, just some, don't confuse it with respect to loss. Okay, now summation over I equals 1 to n. Okay, and then j equals 1 to m. So the same whole value, you just take it, ij log xi parameterized by mu j sigma j plus j equals n ij j plus the constraint. So this will be our Lagrangian j equals 1 to m j minus 1. Okay, so now this will be my optimization equation. So what I should do now, from here it is straightforward. Once you have this, this is straightforward. Now the remaining things is just algebra. Okay, now this has the parameters mu j, sigma j, alpha j. You take each of them and equate it to 0 and obtain the optimal values. Okay, first what I'll do, I'll take with respect to, I'll take the partial derivative of this with respect to alpha j and equate it to 0. Okay, now because of which what will happen, summation I is equal to 1 to n alpha j n of xi parameters by mu j sigma j divided by k xi okay plus equal to 0. Now this will give me summation I is equal to 1 to n mixing coefficients plus go to 0. Therefore my j will be summation I is equal to 1 to n this will be my value. Now what is this? Now I don't know what is this Lagrange multiplier. Now how do you obtain this? Now you know this value and you know the constraint that is there. By using the constraint you can easily get that. Now we have done this already. So in the sense, not this specific problem, similar cases we have done it earlier. Now using the constraint, now what is the constraint? Now if I take sum over all the alpha j's, it will be 1. Put that constraint. Now this will be j equals 1 to m, just have minus 1 over, then this is I equals 1 to n. Now I can interchange the order that is there. So we already know that this is 1. That's what we did it earlier, right? This, you sum it over, so this is k equals 1 to m. Now this you will get it as 1, right? Now I just want to use that specific thing here. Now this will immediately give us, so just make a note of it. We know that if we sum over j equals 1 to m, I get 1. Therefore, I get lambda equals to minus n. Now, which directly imply that alpha j is 1 over n summation I is equal to 1 to n this responsibilities. Okay, this is how I obtain it for alpha j. Okay, now similarly I have to do it for mu j and sigma j as well. So let's do that. Now this is one parameter is done. Now for mu j, now what do you do it? Now you take L, take the partial derivative with respect to mu j and equate it to 0. Okay, so a very straightforward, simple calculations. We have already done this, but it involves a bit more algebra in this case. So now this will be minus summation I is equal to 1 to n alpha j equals 1 to m yeah. So then this is the covariance. So this, we have done this kind of differentiation in detail in our earlier tutorials whenever we are going ahead and obtaining the MLE. Okay, exactly do the same thing. Okay, now you multiply it by the inverse of your covariance matrix, and then what do you get finally? So now you get this, we know. Okay, so this will be equals 1 to n, so minus 1 to n equals to 0. Now this will be j equals is equal to 1 to n okay. So now this, we can say it as some kind of a constant that is there. Now because of which I can say that my mu j is 1 over nk, or in this case better to say it as nj, okay, into summation is equal to into n xi. This will be for mu, and similarly I leave it as a simple exercise to obtain it for the covariance. So I'll just write the result. Similarly, differentiate take the partial derivative with respect to j and equate to 0. Now we will be able to get it. Okay. J equals 1 over nj summation I is equal to 1 to n j xi minus mu j into xi minus mu j, the outer product. Okay. Now this is we have seen similar kinds of derivations earlier. I hope that you will be able to take care of this. Now this is for one specific t, and then you have obtained these parameters. Then what do you do? Now this is the m step. I should have mentioned it. Okay, this is the m step. Okay. Now with these updated parameters, you go back and obtain these values afresh. Use those value, get this, equate each of them to 0, and then obtain new set of parameters and go on repeating this. Now this is your EM algorithm, okay, expectation maximization algorithm. Okay, so I have omitted the T because of too much of cluttering of notations, but I assume that this is pretty much comfortable and clear. Okay, so now just as a side thing, now I just want to do a very small and an intuitive proof of showing that all of us knows the K-means algorithm. Okay, now K-means in the sense it is used for clustering. Now what you shall do is, given a data point, we'll see that what are the distances that is there with respect to all the centroids, that is the mean of a group of data, and then you will assign the data to the nearest centroid of it, and then you recompute the mean again. Now we will be repeating this till the convergence. Okay, this is the idea of the K-means clustering algorithm. Now it can be easily shown that now this GMM, so under certain conditions, it is same as the K-means algorithm. Okay, see, in the Gaussian mixture models, now we see that there is a soft assignment of data to the Gaussian mixtures. But what happens in K-means is it's hard assignment. You say that this particular data belongs to this particular group, this belongs to this particular cluster. Okay, you actually say that. Okay, that is what is known as a hard assignment. Okay, so now let's see how it nicely come out of this. So now, small proof of K-means a special case of GMM under certain conditions. No, for sure. Okay. Now assume that you have M Gaussians. So assume that the covariance of the kth Gaussian is sigma square I. Okay. It's an identity in which only the diagonal elements have the value of the sigma square. Now then, how will you compute this value? Now this will be alpha k into xi mu k sigma k divided by summation j equals 1 to m alpha j n of xi mu j sigma j. So now it actually happens that now since this is scalar multiplied by an identity matrix. Okay, now we can easily obtain this value. This is same as k into exp of minus 1 over 2 sigma square, second norm of xi with respect to the kth component, divided by j equals 1 to m alpha j exp of 1 over 2 sigma square xi minus mu j whole square. So now how it boils down that how will this be a Dirac delta function is what we should actually look at. Okay, so now it is evident and easy to see that as sigma square tends to 0, what happens? Now in the summation, what happens is as it tends to 0, now what will be the dominant value of this summation? Okay, so now to understand that, let's take a point xi, and then you have mu1 and mu2. Now this is the distance, let's call it d1, and this is the distance d2. Now it is evident that x1 is near to mu1. Now because of which, now what will happen is, now you will get in the denominator minus 1 over some beta value d1, now this is the distance, okay, plus exp of minus 1 over beta this d2. Okay, now as this tends to 0, see what happens is the denominator will be dominated by the term which is having the smallest distance. Okay, this is now how this is x goes. Now it is evident that this is, sorry, it's not touching. Okay, sorry for my bad writing. Okay, it reduces, this is e power minus x, right? Okay, so now because of this, as tends to 0, this summation of denominator will be dominated by the term which is very close, so to except from the mean which is very close. Okay, summation of the denominator will be dominated by term with smallest xi minus mu j whole square. Now this is, that's all. It will dominate it, numerator and denominator, it will cancel out, so it will be 1. So now for all L not equal to j, this will be 0. For the one with least distance, this will be 1. This is a Dirac delta function. This is what is known as the hard assignment. You're assigning the value to a specific cluster. Okay, now this shows that under these conditions that we have just looked into, okay, now the K-means algorithm will be So on these conditions, GMM will be the K-means algorithm. Okay. So now this is where we stop this tutorial. Now I hope this was helpful. Now the main idea of this tutorial was to give you an intuitive feel to obtaining the values or the updated values of the parameters and work with them. So we'll meet in the next tutorial. Thank you.